All right, let's get started with our next hazard analysis. We'll get to our PDB. This will be analysis number 9, record number 10. We highlight that record, go to add-ins, EasyHaz PDB menu, load parameters from PDB record. And we get our next hazard analysis. This is a grad student, built this diode laser, 850 wavelength, 800 milliwatts, average power, it's continuous wave. We have some beam conditions. What we knew is that the beam diameter was about 2 millimeters. But all we knew past that was that, well, it was good beam quality. All right, so what we decided to do is take advantage of what we know about m squared. We'll say, well, for worst case, I'd like to know the lowest divergence or smallest divergence angle that is theoretically possible for a laser with a wavelength of 850 nanometers and a beam diameter at the waist of 2 millimeters. Again, this is a circular Gaussian and 1 over e squared points. So what we do is we load in the 2 millimeters and we come down here and we put the m squared limit, which is our theoretical limit, to 1. It will calculate the lowest divergence possible, and that's how we treat lasers when we only have part of the information. We go for worst case, and in this case, worst case meant 2 millimeter beam diameter, 1 for the m squared diffraction limit, which is the theoretical limit. Let's take a little bit of look at some of the results here. OD at observer range and worst case are identical. That's because the beam diameter, 2.02 at a half a meter from the beam waist, still gives us 100% transmission through the limiting aperture being, that's right, 7 millimeters. Our ocular MPE is 2 milliwatts per square centimeter, and our skin MPE is 0.4 watts per square centimeter. So let's go up here and look at our NOHD, which is 590 meters. Let's look at our skin hazard distance, and yeah, it reduces significantly because it's a much higher MPE for the skin than for your eye. So this makes sense that the nominal skin hazard distance would be much shorter, again, as we've seen in some of the previous examples, than the nominal ocular NHD, which is at 590. All right, so really the point of this particular example is to understand that when we only have a little bit of the information, what we do is we use m squared, and we'll set m squared to 1, and then usually it's adjusting the beam diameter and letting the system calculate the divergence for us. Remember, divergence is really what plays into the nominal ocular hazard distance, or the NOHD. So we like to set the divergence as low as possible, so we're looking at worst case NOHD and OD at observer ranges. What if we didn't have any information? We don't know what the diameter is. We don't know what the divergence is. What we like to do in that case is set this to 1 millimeter and set the m squared value to 1. Okay? And what this is going to do is okay, I didn't know anything, so I set it to a reasonably small diameter, and let the system calculate the divergence. And so when it does, this is the theoretical limit to the divergence for this beam diameter. And so it does change the problem. We'll notice that the eyewear doesn't change much because we're still pumping the same amount of power, getting 100% transmission through the limiting aperture, but the NOHD changes because the divergence changed from what our previous data had. So what I'm going to do is I will go back here. I'm going to reload this hazard this record. Gets us back. Again, these OD values, 3.018. What eyewear do I buy? OD3. Okay. Still not 3.1, so I'm not going to round up yet. Right. Let's see, what else can we point out? Well, I could take a look and ask myself, does the OD make sense to me? I can come over here and look at the average irradiance in the limiting aperture. The average irradiance is just a little over 2 watts per square centimeter. So that's 3 orders of magnitude greater, 3 orders of magnitude, almost exactly 3 orders of magnitude greater than the MPE, and that is reflected, sure enough, in the OD being 3, which is your 3 orders of magnitude difference between the average in the limiting aperture, average power in the limiting average irradiance in the limiting aperture, and the MPE. Okay, I think that's about it for this one.